a few things that I saw in this mock test. I looked over and did the whole test this past weekend. And some of the things we haven't covered very well, but probably over 90% we've covered. I wanted you to look at a couple things. First of all, derivatives of an ln function, which is a natural logarithm. And if we have, I kind of miswrote this. I meant to put, if you have the derivative of the logarithm, okay, of, say, x squared, 20x squared plus 2x. What this is, the answer to this, the derivative, is the derivative of the top. In this case, is going to be 2x plus 2 over the bottom, or over the original. So derivative of the original over the original, that's going to be the derivative of a logarithmic function. Okay, so if we had, just to make another example, if we had, if we want to have the derivative of, let's say, the logarithm of cosine x. Okay, what we would have for that is we would have the derivative of cosine x, which is negative sine x, over the original, which is going to be cosine x. And so this will simplify to negative tangent x. Okay, so anyway, that's what we're looking at. Now, kind of the converse, the integral of the 1 over x functions, or we could sometimes call these as x to the negative 1 power functions. So in this case, if we have the integral of 1 over x minus 2, as a matter of technicality, we would do a u substitution. We'd have let u equal x minus 2, but practically what we can do is just take the logarithm. I think we say the absolute value of the logarithm. I think it's the logarithm of, hang on a second, logarithm of absolute value of x minus 2 plus c. And if we demonstrate that this thing in fact is positive, if we take, let's do the opposite operation. Let's take the derivative of the logarithm of natural log of x minus 2 plus c. What are we going to get? Well, we're going to get the derivative of x minus 2, which is 1, over the original, which is x minus 2. And then the derivative of c is going to be 0. So we can tie in that if we ended up finding the integral, but then we took the derivative of that integral and came back to find what we had the original before the integrating. So there are a few problems involving this principle that we haven't covered a whole lot. We've just barely touched upon it. We're going to do more these last few weeks, but I wanted to show you that before our test tomorrow. There's going to be a speed increasing problem, and this is toward the last part of the calculator multiple choice section. And specifically, the one that really got to me was this one here, this 3 to the negative t power, because typically we've seen the e to the negative t or negative x, but we haven't seen the 3. So that's a situation that I think it's been very seldom tested in these AP tests over the past few years anyway. So I wanted to briefly take a look at it. And basically to solve this problem, this is from the calculator portion, if you go ahead and plot, graph this function right here, the velocity function, you're going to see a function where I think you're starting positive and going negative, and so using the critical number, which we found the 0 on the number line. In fact, what the graph of that looks like, I believe, is something like this, where you have a graph coming down like this, and then goes down, and this critical number here is going to be 2.0050. And so now this is the graph of the derivative, v of t. Right? That's not the original function. And so if we have positive to the left of 2.050 and negative to the right. And so this is what our number line analysis would look like. Now, where we're getting into trouble is this next section, that we're trying to find the speed of the particle increasing. Well, we need to analyze the velocity, which we did on this first number line. But to analyze the acceleration, we have to take the derivative of the velocity. Well, these first two terms, this -1/2 t cubed and t squared, we know how to take the derivative of that. But this next one, this plus 2 to the negative t power, what that becomes is we have the derivative, I'm going to put dt of 3 to the negative t power is going to equal 3 to the negative t power, but using the chain rule, we have to take the negative sign because the derivative of negative t is -1, and then we have times the natural logarithm of 3. And so that's where this thing comes from. And so once you have this, and this last term is a critical one that we really haven't covered how to do, and basically it's like the e to the x thing, except we have to multiply by the logarithm of that base. All right, so if we had e to the negative t, we would have to multiply by the logarithm of that base, which would be ln ln which would cancel out. See? So that's why that's a distinction. So we haven't looked at this particular distinction. And then, with that in hand, you can graph and find a 0. And I think when you graph, the deal looks like this. You have a graph, and the thing starts, I think this thing starts negative, if I'm not mistaken, and goes up through this critical number, which is 1.702. And then what that does, we can do a number line analysis where we have the concave down from 0 through 1.702, and we have concave up thereafter. And so where is the function increasing? Well, we have this is the arrangement we have. And so if we combine these two number lines together, over this interval right here is where we have the concave up, and the position, speed of the particle is velocity is positive. And so we say on the interval, we're going to say 1.702 comma 2.05 2.050. And why? Because the signs, the signs of v of t and a of t are the same. Okay, this is again a calculator, graphing calculator problem, and one reason you can tell graphing calculator problem is something I'm going to show you at the end. Now, in the free response section, the very last problem in the non-calculator portion is something like this. We have we call a differential equation, dy dx equals 2 over x squared times quantity y minus 2. That's a problem similar to that. And so it says the first part of the problem says let f of x be a particular solution of the differential equation that contains the point 1 comma 3. Find dy dx at that point. So all we have to do for this one is we plug in our values of x and y. So dy dx is equal to 2 over, well, 1 squared, which is 1. I'll just put 1 squared times quantity 3 minus 2. And so if we take 2 times 1, that equals 2. So dy dx is equal to 2. And then there's going to be what we call a slope field thing where you're asked to find the slope of different points. So you have a grid here with 9 points, one of which is going to be this 1 comma 3. Okay, in that case, you know that the slope is 2, so you draw a little slope, and then you have all these other points with these dots, and for these, you need to plug in these numbers. There are 9 of them total. I mean, x and y values, and you're going to get these little, and you draw these little slopes, a little hash line that represents the slope. Now, we haven't really gone over these. I would just ignore it if you really can't make sense of it quickly. But then the next part is where you find the particular solution at y equals f of x at the point 1 comma 3. And so for a particular solution, I'm going to erase all this that I did for this first part. And this first part that I did, where we got 2, that's just 1 point, but that's, every point can help. Find the particular solution. And what you're doing here, the first thing they're looking for is separating the variables. And to do that, we have all the x-related stuff on one side of the equation and all the y-related stuff on the other side. And to do this, we take dy, we multiply both sides of the equation by dx and divide by this quantity y minus 2. So we're going to get dy equals y minus 2 equals, we have 2 over x squared times what we multiplied by dx. And you get 1 point for this thing, which is called separation of variables. Okay, the next thing we need to do to solve this equation is to integrate both sides. And so if you have this variable separated, that's 1 point. The next thing they're going to look for is to see this when you're integrating both sides of the equation. And what you're going to have when you integrate this left side, you remember back from, we looked at the integration of a 1 over x situation. This is going to be 1 over y. And so on the left side, we're going to get the natural logarithm of absolute value of y minus 2. And we would normally put plus c, but we're going to do the plus c on the right. And on the right side here, we're going to have the integral of 2 to the negative 2 power, right? So 2 over x squared equals 2x to the negative 2 power. And taking the integral of this, we're going to raise by 1. So we're going to get 2x to the negative 1 power, and we're going to divide by this, what we raised to, which was negative 1, which is going to make this negative, which is going to be equal to, oh, I forgot the plus c. Now we had a plus c from the left side when we did this integration, and on the right side we just sum it all up in 1, and that's going to be equal to negative 2 over x to the plus c. Okay, the next thing we're going to do is solve for y. And to do that, we realize that we're going to have a positive value here. So the absolute value of y minus 2, that's going to be positive. When we plug in 3, that's going to make this thing positive. So I'm just going to put in ln just y minus 2 equals negative 2 over x plus c. Now to solve for y here, what we're going to do is take the, we're going to take e to the power of both sides, and the e, let's see, e to the power of, on the left side, e and e to the power of log base e, or natural logarithm, is simply going to be y minus 2 is equal to, let me do one thing first. One crucial thing first before I go there. We're going to go plug in this 1 comma 3. And so to find what c is. So we have ln, and that's going to be 3 minus 2 equals negative 2 over 1 plus c. And so we're going to have ln of 1 is equal to, was that negative 2? Yeah, negative 2 over 1 is equal to negative 2 plus c. So if we add 2 to both sides, actually ln 1 is 0, because what does e have to be raised to? What power does e have to be raised to equal 1? Well, 0. So we get 0 equals negative 2 plus c. So we say c equals 2. And we take this c equals 2, and so we have, I'm going to rewrite this over here with c equals 2. So we have ln of y minus 2 equals negative 2 over x plus 2. And now we're going to exponentiate both sides of the equation. So we have e to the power of ln and e to the power of negative 2 over x plus 2. So we get is y minus 2 is equal to e to the negative 2 over x plus 2 power. And that's the specific equation. If we want to rewrite this and solve for y, we get y equals f of x equals e to the power of negative 2 over x plus 2, and then we're going to add this 2 over here from the left side, plus 2 here. And so there's going to be a point distribution all along the way on this problem, this last problem. You're going to have to separate the variables, integrate both sides, go ahead and substitute in the point, in this case 1 comma 3, to solve for c. Once you solve for c, you go back and get the particular, substitute in 2 for c, and solve the equation for y, and you've done it all. So That's a good problem, the last one on the free response section. All right, the calculator section. Calculator section is 50 minutes and is 17 problems. And I went and counted the problems. These two problems right here, this one, problem 2, and problem 10, were from our last test. And you can tell that it's a legitimate calculator problem if you have these decimals with 0.314, for example. When you have this kind of detail, the calculator is the only thing that's going to be able to give you that kind of accuracy. So that lets you know it's a calculator problem. Another problem would be like this one, problem 10. That's an example of a calculator problem. There can be other problems in the calculator section that have numbers in them, but really are not calculator problems because the numbers they have are ones are going to be like whole numbers and ones that you could calculate pretty easily without using a calculator, some of them. So you look out for that on the 7 of the 17 that I see on that calculator multiple choice are really calculator problems. And let's see, anything else? Yeah, there's going to be a problem that looks very much like this one. The particle moves along the x-axis, velocity of particle. Now this is from the calculator multiple choice section and is really not a calculator needed calculator problem. It's just examining your understanding of how to find averages, and finding averages you really find it one of two ways. In this case, the average rate of change. Well, this one right here for E is not the average velocity, that's the average position, right? Because you take, anyway, it could be the average position. I think this answer to average velocity of the particle, you take the velocity equation and you take the integral of that in 1 over 8, which is 1 over b minus a. So I think in this instance, our answer is going to be B. But you're going to have a problem almost exactly like this, and you're going to have opportunities to do AROC, or you have to test your analysis skill, not your calculator usage skill. And then this one also from the calculator portion, I believe, is this is from our last test. The one that's going to be on your mock exam is going to be very, very similar to this one, except I think it's going to have a third thing where they're going to give you a reverse order, and so you're going to have to take the negative sign when you take that all into account. And so you're going to have to work all that out. Anyway, this is a preview to what you're going to be looking at tomorrow. I thought really quite a challenging test for the multiple choice section. Not pretty much because it had, I didn't see a lot of real easy problems on it, because most of the ones I've seen in the past will have what I think are more easy problems. The free response section I didn't think was so bad. So, but again, this, like all the tests we've had, this mock exam is going to be a learning example. You do your best, and if you do your best, you put yourself in a position to learn as much as possible when we have our review. And you're going to need to do that through the end, even through the actual AP test that you take some few weeks from now. So good luck. I've given you what I've felt that I could, and I thank you for viewing.